The last instrument we're going to talk about is the Michelson interferometer. Most of us are not likely to ever work on such a device, but it's really, really cool, and it's been in the news lately. In the last couple of years, the scientists have been talking about measuring gravitational waves, and this is exactly how they do that. So the Michelson interferometer basically uses optical interference in order to be able to pick up very, very small waves. This is the LIGO facility for the interferometer in Richland, Washington. So out in the desert, basically. And there's two arms here that we bounce the light off of that are several miles long. And they have to be perfectly straight lines, but all the action happens in the facility right here. In fact, many of these sites are populated all over the world at this point. We have two in the United States, one in Washington and one in Louisiana. And then there's a couple in Europe, one in India, and one in China, so that we basically have the world covered and are hopefully able to see gravitational waves no matter what direction they're coming from. So here's one of the first measurements of a gravitational wave, and they're able to match these with simulations and be able to figure out what two types of things are colliding, if it's two black holes, if it's two neutron stars, whatever. But they didn't have this thing on very long before they saw several gravitational waves. So these are happening all the time, and it gives us another lens very, very deep into space, because gravitational waves can pass through everything, so we don't have the problem of not being able to see through the Milky Way galaxy to be able to see on the other side and get even more data for the future. So how it works is we have basically a light source that is split by basically a half silvered mirror. Part of the light ray goes down one arm and comes back, and the other part goes down the other arm and comes back. And these are precisely measured, that we get an interference pattern when we return. And if either one of these arms changes in length by less than the size of a single proton, then we'll be able to see that and be able to measure the gravitational wave. So this is an extremely precise instrument and is able to measure things far smaller than any other instrument that we're able to have on Earth. The interference pattern of the two rays is the difference of their path lengths. When one of the mirrors is moved a distance of lambda over 4, we get dark fringes. So this is called a fringe shift, and the wavelength can be measured by counting the number of phase shifts that we have. If the wavelength is accurately known, the mirror displacement can be determined within a fraction of a wavelength, which is really cool. So, for instance, we'll do a little bit of math, is the change in length is equal to n, the number of fringes, divided by lambda over 4, or the cycle. So number of fringes versus cycle is twice, so it depends on what you have. So for this interferometer, one of the mirrors has moved 25.8 micrometers, and certainly they do make these on a smaller scale than the LIGO machine. And 92 bright fringes are counted on the screen. So we're going to solve this for lambda is equal to 2d over n, gives us 2 over 92, because we saw 92 fringes, times the slit width is 25.8 times 10 to the negative 6 meters, gives us 0.561 micrometers.